Hello everyone, and welcome again to Nettle, the best platform around for distance learning in business, finance, economics, and much more. Please don't forget to subscribe to our channel and click that bell notification button below so that you never miss fresh videos and tutorials you might be interested in. Many thanks to our current Patreon supporters and YouTube members for making this video possible, and we'd also greatly appreciate if you consider supporting us as well. So please check the link in the description and click the join button below for more details. My name is Seva, and today we're continuing to investigate marked efficiency test implementations in Python, and today our main hero is the variance ratio test, one of the most frequently applied tests for market efficiency that can quite flexibly determine whether the stock price series you're investigating is mean-reverting, trending, or indeed efficient. And we'll look at how to flexibly implement it in different timescales and how to apply the Chow-Denning multiple testing correction. So first, let's discuss the packages that we'll need for our today's code and build it from scratch alongside. So first we need to import NumPy as NP to work with arrays, pandas to work with data frames, yFinance, the Yahoo Finance package for data downloading. Then we'll also need SciPy stats for hypothesis testing, and matplotlib pyplot for some visualizations. Now let's specify our sample and our time series of interest. So first, let's start with S&P 500, the JSPC ticker from Yahoo Finance, and let's specify our start and end dates. And let's go for a 10-year period from year-end 2011 to year-end 2021. And then we can already get our data down the line using the Yahoo Finance download function, specifying the ticker, the start, and the end. And as we only need the closing adjusted prices, adjusted for dividends, so the total return index, we can specify the adjusted close to not worry about other candles. And now we can check that our data downloading has been correct. Indeed, we start at the beginning of 2012 with the value of S&P 500 around 1200, and we end at the year end of 2021. And now we can specify our returns series, which can be quite efficiently calculated using the percentage change function from pandas. And then, as the first observation would be an NA by default, we can only start from the second observation. And that, if we look a little bit closer, calculates returns day by day correctly, removing the very first day when the return date is not available. And we have got more than 2,500 observations. Then let's specify the longest window we will be interested in calculating the variance ratio statistic for. And let's denote it max T. And it all depends on the time horizon you're interested in, but in the literature it's generally common to limit your max T at 64. Usually we're interested in powers of 2 for the reasons as that would allow us to cover multiple time horizons in very limited number of tests, but here we'll move from T equals 2 to T equals 64 sequentially and compute the variance ratio statistic for each and every of the max T or T parameters and look at the dynamics of the variance ratio across time to determine when any of the trending or mean reverting behavior, at which frequency it's most observable, it's most prominent. And now we can calculate the not variance, the variance of daily returns that will compare our cumulative return variance to for the variance ratios. And here again, pandas built-in functions are very useful, as we can simply apply the var function to the returns series to calculate the variance of daily returns in one go. And then we will simply initialize an empty data frame, which we'll call variance ratio output, and denote that it would be an empty data frame that would assemble the results for our testing for each and every of our time frequencies of interest. And then we'll move in a loop for t in numpy range. And obviously, we're interested in time starting from 2 days, as that's the lowest time you can calculate cumulative returns for. And we'll end at max t plus 1, so that we take 64 inclusively. And for each and every of these particular time windows, we'll need to calculate cumulative returns, which are going to be the rolling sums of our returns. Again, variance ratio test mostly works with cumulative returns instead of buy and hold returns, albeit the results would not differ much really, regardless of what you apply. But we'll stick with the conventional way of estimating it using cumulative returns. So sums of rolling returns. And here, the rolling function for pandas is quite useful. So we'll calculate our variance, which is just the variance for cumulative returns over t days, is going to be the returns rolling t, which specifies the length of the rolling window that we want to calculate something for. Then we specify that we want to calculate the sum for this rolling window. And then we specify that we want to calculate the variance of this particular rolling window. And as pandas is not particularly sensitive to NA terms, this would correctly calculate the variance that we care about. So that is the variance that goes on the numerator for our variance ratio, and it means that we can actually already calculate the variance ratio test statistic. And the variance ratio is going to be our variance in the numerator divided by t times variance naught in the denominator minus 1. And here it's a good place to discuss the concept behind the variance ratio test statistic. We generally, if we assume the random walk hypothesis, the independence hypothesis that is, we can quite reasonably assume that variance scales linearly. Variance of t-day returns should be t times the variance of daily returns. That's why when we want to annualize variance, we multiply daily variance by 252, as there are 252 trading days in a year. Here we implicitly have assumed the random walk behavior, market efficiency, the independence of daily returns. However, if we compare what is really going on in terms of the ratio between t-day variance and daily variance, we can explicitly test the random walk assumption that led us to annualize variance that way. And if this variance ratio, this particular expression, is very close to 1, then our time series behaves very close to a random walk, to an independent process. And if it deviates a lot from 1, either in the positive direction or in the negative direction, we can be reasonably suspicious that the random walk hypothesis is violated. And that's why we subtract 1 here, to calculate the deviation from the null hypothesis of efficiency, of independence. And to calculate the standard error of such a deviation, well, we can look at a standard formula provided by Lo and MacKinlay, which has to do with the time horizon t that we care about. So for the standard error, in the numerator, we have got 2 times t minus 1 times t minus 1, and then in the denominator, we would have 3 times t times n. And n can be calculated quite reasonably as the length of our returns. And then, as we have calculated the variance using this particular procedure, we can then calculate the standard error quite simply by taking a square root, raising it to the power of a half. And that, quite intuitively, leads us to calculate the z-stat, which is the variance ratio divided by the standard error. And using the SciPy stats package, we can do the hypothesis testing. So the p-value is going to be 2 times, as our test is two-tailed necessarily, times 1 minus SPS norm CDF, cumulative distribution function for the normal distribution, of the absolute value of the z-stat. And then we are ready to assemble one entry into our variance ratio output data frame, and we can code it as the following. Variance ratio output for time t equals an array where we would enter our var naught, which is our one-day variance, variance ratio, z-stat, and p-value. And here, quite importantly, we can round these entries so that our data frame is more readable, more interpretable. So let's round all of the entries and leave just 6 decimal places. The only one we'll leave unrounded is the p-value, for reasons I'll explain later. So now we can run this code and look at what the variance ratio output data frame has to offer. And we see that here we have got our data frame with each column representing a particular time interval that we take to calculate the variance ratio. And we see that the z-stat for t equals 2 in particular is negative and quite large in magnitude, negative 8.55. That corresponds to a very small, quite close to 0, p-value. However, given the fact that we have undertaken 63 tests here, from 2 all the way to 64, we need to adjust for multiple testing. What is the probability that such a significant result emerged out of 63 63 multiple testing procedures by random chance alone? So here is what we will do. We'll implement the Chow-Denning multiple testing adjustment procedure by retrieving the minimum p-value and the corresponding z-stat, and then performing the adjustment. So the minimum p-value is going to be the minimum of the 4th row of our data frame, which can be retrieved as variance ratio output iloc index location 4. And then we can look at what this minimum p-value is and see that it's quite close to 0. It's astronomically small, if you will. And then we can calculate the Chow-Denning p-value adjusted for multiple testing using the 1 minus minimum p-value raised to the power of max t minus 1, as max t minus 1 is the number of hypotheses that we have tested for. And then to determine whether our series is trending or mean reverting, depending on the sign of our z-stat, provided that Chow-Denning p-value is statistically significant, we can calculate the maximum z-stat, which is going to be the entry from the 3rd row of our variance ratio output data frame. So we can still use the iloc here, but only if our p-value, which is variance ratio output iloc 4, equals minimum p-value. And that needs to be converted to values, and just in case there are multiple entries that generate the same p-value, that's quite improbable, but who knows, we'll just retrieve the first element, the lowest time frequency when this happens. And that means that now we can build some interface to determine whether our time series is trending or mean reverting. So first of all, if our Chow-Denning p-value is greater than 10%, then the results are insignificant, meaning that no deviations from the variance ratio of 1 are significant, and that means, in turn, that our time series is serially independent. Our returns are not causing future returns, and that means that the market is efficient and adhering to the random walk hypothesis. So here we can print that the market is efficient. However, if it's not the case, then we can use the elif function and look at the sign of our z-stat. So elif max z-stat is positive, we can conclude that the market is trending. Why? Well, it has to do with the deviation from the unity variance ratio statistic. If our t-day variance is higher than what we would expect for an independent time series, it means that disturbances that are notable in returns accumulate, are exacerbated via the trending behavior of the time series. And that leads to us concluding that the market is trending, or persistent, if you wish. Else, if the z-stat is negative and the Chow-Denning p-value is significant, we then conclude that the market is mean-reverting, or anti-persistent, simply given the fact that if the variance, the disturbances of daily returns are smoothened out, are less prominent on a larger time horizon, it means that there is oscillating behavior in individual daily returns that smoothen cumulative returns out. And that is the reason why, in this case, we conclude that the market is mean-reverting or anti-persistent. And finally, we can use our PLT plot function to visualize our z-stat over time. So we can plot the variance ratio output I log 3, which is our z-stat. And we can run the code and see that the code concluded that S&P 500 is mean-reverting or anti-persistent. And here is the dynamics of our z-stat. We start very low, below -8, as we have seen in the output data frame in the table that we seen quite a bit ago. And then the z-stat increases and then levels off at around -3, which is enough evidence, even after accounting for multiple testing, that our market is indeed inefficient, doesn't follow a random walk, and is anti-persistent or mean-reverting. And the beauty of this code is that we can enter any individual stocks or even indices and quite efficiently and quite quickly test for efficiency in those. So for example, if we take Walmart, we can verify that it's indeed anti-persistent as well. However, not to an extent S&P 500 is. And we can see that it doesn't level off really. If we look at higher time horizons, there is an upward slope in the z-stat later on. However, the z-stat for smaller time horizons is quite high in terms of magnitude and negative. So -4 is again low enough for us to conclude that the series is mean-reverting. Also, the chart that we have over here tells us where this mean-reverting behavior originates. We can see that this particular behavior is quite short-term. The lowest z-stats are associated with the smallest values of t, which is not always the case, but is quite common when you're looking at stock returns. Then we can look at some another well-established stock like Caterpillar and conclude that for Caterpillar, the market is efficient. We have got the lowest of our z-stats that hints towards anti-persistence, if anything, around 35 days over here. However, the deviations from zero are quite small, and accounting for multiple testing as well, we conclude that Caterpillar is indeed an efficient market, which is, again, not necessarily that surprising given how well established and mature the market is for Caterpillar. And if we input some other stock, like Boeing, we can quickly see that not all US stocks are efficient or mean-reverting, with Boeing being a very notable example of persistence or trending behavior. And here we see that the most evident trending behavior is indeed not observed on t equals 2, but on some mid-term time horizon, like a weekly persistence. And also we can look at other stock markets like the UK. This is a notable UK index. And we can see that the UK market is characterized by persistence, whereas the US market is characterized with anti-persistence. And that's something that we have also verified in our previous video on runs test in Python. So check this out if you're interested in another market efficiency test implementation in Python. And finally, we can check the Japanese stock market, Nikkei 225. And here, just as for our runs test result, we conclude that the Japanese market overall is efficient. And that's the implementation of variance ratio test with the Chow-Denning multiple testing adjustment in Python. Please leave a like on this video if you found it helpful. In the comments below, I'm eager to see any further suggestions for videos in business, finance, or economics you would like me to record. And please don't forget to subscribe to our channel or consider supporting us on Patreon. Thank you very much, and stay tuned.